प्यारे बच्चों, ਅੱਜ ਦੇ ਪਾਠ ਜਨਰਲ ਆਰਗੈਨਿਕ ਕੈਮਿਸਟਰੀ ਵਿੱਚ ਤੁਹਾਡਾ ਸਵਾਗਤ ਹੈ। ਅੱਜ ਅਸੀਂ ਕੁਝ ਆਰਗੈਨਿਕ ਫੰਡਾਮੈਂਟਲਸ ਤੇ ਵਿਚਾਰ ਕਰਾਂਗੇ ਜਿਨ੍ਹਾਂ ਨੂੰ ਆਰਗੈਨਿਕ ਰਿਐਕਸ਼ਨਸ ਦੀ ਸਟੱਡੀ ਵਿੱਚ ਯੂਜ਼ ਕੀਤਾ ਜਾਂਦਾ ਹੈ। ਅਸੀਂ ਸਾਰੇ ਜਾਣਦੇ ਹਾਂ ਕਿ ਆਰਗੈਨਿਕ ਕੰਪਾਊਂਡ ਕੋਵੈਲੈਂਟ ਹੁੰਦੇ ਹਨ। This is due to fact that carbon in its excited state has 4 bonding electrons which it shares with electrons of other elements and forms 4 covalent bonds. As carbon forms covalent bond, organic compounds are mainly covalent in nature. Organic reactions are therefore reactions of covalent compounds which are generally complex in nature. These are involving more than one step and the reaction has a proper mechanism. In order to understand mechanism of any organic reaction, we must know some basic fundamentals which decide the course of reaction and help in predicting the right or major product of reaction. Moreover, organic acids and bases are generally weak. The strength of these depends upon electron displacements in molecules which decide their strength. In order to predict the acidic and basic nature of these compounds, we must know various types of electron displacements. ਅੱਜ ਦੇ ਵਿਸ਼ੇ ਦੇ ਵਿਸਤਾਰ ਵਿੱਚ ਜਾਣ ਤੋਂ ਪਹਿਲਾਂ ਆਓ ਅਸੀਂ ਅੱਜ ਦੇ ਵਿਸ਼ੇ ਦੇ ਲਰਨਿੰਗ ਆਬਜੈਕਟਿਵਸ ਜਾਣ ਲਈਏ।
Upon completion of this topic, the learner will be able to understand types of electron displacements, define reaction intermediates and their types, predict stability of intermediates, provide right order of acid and basic strength of organic acids and bases.
Dear students, ਆਓ ਸਭ ਤੋਂ ਪਹਿਲਾਂ ਜਾਣਦੇ ਹਾਂ ਕਿ ਕੋਵੈਲੈਂਟ bonds ਕਿੰਨੇ ਤਰ੍ਹਾਂ ਦੇ ਹੁੰਦੇ ਹਨ ਅਤੇ ਕਿਵੇਂ ਬਣਦੇ ਹਨ। Yes, these are formed by overlapping of valence atomic orbitals of 2 atoms which contain unpaired electron of opposite spin. This is the view of valence bond theory. According to this view, about internuclear axis overlapping of orbitals can be of 2 types which led to the formation of 2 types of bonds. These are sigma bond and pi bond. इन्हां दोवां bonds which are sigma bond relatively pi bond to ज़्यादा strong हुंदे हन। Children, let us now learn about the breaking and forming of bonds. We all know that organic reactions usually involve the fission and formation of covalent bonds. The covalent bond is often represented as a dash as shown on the screen, and the movement of a pair of electrons is shown by a curved arrow, whereas the movement of a single electron is shown by fish hook arrow. Let me now tell you that there are 2 ways in which a covalent bond may be broken.
Let us first learn about homolytic fission. Let atoms X and Y are bonded through a covalent bond. When a bond breaks in such a way that each of the atom retains one of the bonding electrons, the process is called homolytic bond cleavage or homolysis. This homolytic fission results in the formation of free radicals.
Let us now learn about heterolytic fission. Do you know that this type of a cleavage is generally found in those molecules in which the atoms bonded to each other are having difference in electronegativity? In such bond cleavage, the bonded pair of electrons move towards more electronegative atom, thereby more electronegative atom gets negative charge and less electronegative atom gets positive charge. Clearly in such cleavages, there is formation of charged species. The ions of carbon formed in heterolytic cleavage are known as carbanions and carbonium ions are of special importance in organic chemistry. Homolytic reactions are typically carried out in the gaseous phase or in solvents whose principal function is to provide an inert medium in which the reacting molecules can move about. Heterolytic reactions are typically carried out in solution in polar solvents. because of the greater ease of separation of charges therein, and very often because of the stabilization of the resultant ion pairs through solvation. Now we will discuss about various types of electron displacements in organic molecules. Electron displacement in organic molecules. In organic molecules, different reactions depend on the electron density in their molecules. Since majority of attacking reagents are polar, therefore in organic compounds, permanent or temporary polarity is developed by temporary or permanent electron displacements. The different electronic effects which operates in covalent bonds are inductive effect, electromeric effect, resonance effect, and hyperconjugation. Now let us study the details of these effects operating in molecules. Let us first learn about the inductive effect. In a covalent single bond between dissimilar atoms, the electron pair forming the sigma bond is never shared absolutely equally between the two atoms. It tends to be attracted a little more towards the more electronegative atom of the two. For instance, in an alkyl chloride, the electron density tends to be greater nearer chlorine than carbon, as the former is the more electronegative.
Have a look at the structure represented on the screen. If the carbon atom bonded to chlorine is itself attached to further carbon atoms, the effect can be transmitted further. For example, in C2H5, Cl, the effect of Cl on C2 is less than the effect of Cl on C1 as shown on the screen. It decreases as the distance from source, that is the more electronegative atom, increases. From practical point of view, it may be neglected after third carbon atom. From this discussion, inductive effect may be defined as the permanent displacement of electrons forming a covalent bond towards the more electronegative element or group present in a molecule.
Inductive effect is denoted by the symbol I and represented by a straight arrow, the arrowhead pointing towards the source. Atoms or groups which attract electrons more strongly than hydrogen are called electron attracting or electron withdrawing groups and produce -I effect. For example, groups such as halogens, carbonyls, carboxylic acids, acid chloride, etc. are having a -I effect in molecule. Different groups do not have same magnitude of -I effect. Let us have a look at the decreasing -I effect of some common groups on the screen. Similarly, atoms or groups which attract electrons less strongly than hydrogen are called as electron-releasing or electron-repelling groups and produce +I effect. For example, methyl, ethyl, etc. आओ हुन inductive effect दी applications ते नजर मारिए. Applications of inductive effect. Let us take up the first one. It helps in predicting stability of charge intermediates. In such intermediates, higher the charge, more is energy and lesser is stability. Therefore, any factor which tends to decrease the magnitude of charge will stabilize the intermediate. For example, stability of positively charged carbon, that is, carbonium ion or carbocation, increase in the presence of groups with +I effect and decreases in the presence of groups having -I effect. आओ हुन dipole moment बारे जानिए. Since inductive effect leads to a dipolar character in the molecule, it develops some dipole moment in the molecule which increases with the increase in the inductive effect. Let us have a look at few examples on the screen. The dipole moment of methyl chloride is 1.83, which is more than that of methyl bromide, which is 1.79, which again is more than methyl iodide, which is 1.648D. Let us now discuss about bond length. With increase in inductive effect, the bond length usually decreases because of increased ionic character. Let us have a look at the figures on the screen. Let us now discuss about the strength of fatty acids. We must know that all organic acids are mainly weak acids. The strength of these weak acids mainly depends upon stability of its anion form. Greater the stability of anion form, stronger is the acid. As anion is negatively charged species, therefore, groups with plus I effect increases the magnitude of negative charge and destabilizes the anion. On the other hand, groups with minus I effect stabilizes the anion by decreasing the magnitude of charge. Hence, in such acids, groups with plus I effect decreases the acidic strength and groups with minus I effect increases the acidic strength. For example, the strength of formic acid, acetic acid and propanoic acid is different due to inductive effect of the group attached to COOH group as shown on the screen. Similarly, in substituted acid, strength depends upon the effect of the group attached. For example, chloroacetic acid is stronger than acetic acid as chlorine atom has minus I effect and it stabilizes the corresponding anion formed. Larger the number of chlorine atoms, the greater will be negative inductive effect and the stronger will be the acid. You can observe these structures on the screen. In the first case, where there are 3 chlorine atoms, there will be more negative inductive effect than in the second case where there are 2 chlorine atoms. In the third case, we find that only 1 chlorine atom is there, and in the last case, there are no chlorine atoms. The relative strength of the different halogen substituted acids is as shown on the screen, as fluoroacetic acid is more acidic than chloroacetic acid, which is more acidic than bromoacetic acid, which is turned in more acidic than iodoacetic acid. Let us now discuss about the second effect, that is electromeric effect. In any unsaturated molecule or molecule having multiple bonds, the close approach of a reagent deforms the electronic system of molecule at multiple bond. When the reagent is removed without allowing the reaction to take place, the electronic system reverts to the original ground state of the molecule. This kind of polarizability of multiple bonds is known as electromeric effect. This effect is observed only in molecules with multiple bonds and it is an effect of pi electrons. This effect causes complete transfer of the pi electrons from one carbon to the other. Consequently, one end around multiple bond become positively charged and the other negatively charged with the aid of attacking reagent. The shift of the electrons is shown by a curved arrow indicating the direction of the electron shift as shown on the screen. The effect is temporary since the electrons revert to the original state on removing the reagent. When the multiple bond is between two dissimilar elements, the shift of electrons take place towards the more electronegative of the two. In this case, oxygen is more electronegative than carbon and the shift of electrons takes place towards oxygen. In the second case, nitrogen is more electronegative than carbon, so electron shift takes place towards nitrogen. Inductive effect may also determine the direction of the shift of electrons shown on the screen. Let us now learn about resonance. Whenever in a molecule the electrons of pi bond are in conjugation, with either a second pi bond or with an atom which possesses a pair of electrons in a p orbital, it exhibits a phenomena of resonance. Such molecules show an electron displacement of pi electrons through resonance called resonance effect. This effect is possible only if in a molecule there is conjugation of electrons. Various groups in which electron displacement is through conjugation can be of two types: groups with plus m effect and groups with minus m effect. Now, we will discuss different types of conjugation of electrons and effect of the group attached. Let us begin with the first one, that is pi bond conjugation. इस type the conjugation the example butadiene है. You will find that in this molecule there are two double bonds at alternate positions. The pi electrons in this molecules are in conjugation and this molecule exhibits resonance. This is a symmetrical molecule and conjugation does not lead to the appearance of a dipole. In valence bond language, contributions from the ionic structures shown on screen are necessarily equal and their dipoles therefore nullify each other. This is not true, however, when pi bonds of different types are in conjugation. For example, in an alpha-beta unsaturated carbonyl compounds such as but2enal, the contribution of structure A is greater than that of B because oxygen is significantly more electronegative than carbon in the carbonyl group, thus polarizes the carbon-carbon double bond. Such a group which withdraws electrons from an adjacent group via the pi bonding framework is described as having a minus m effect, the negative sign indicating electron withdrawal. Other groups having this effect include ester, nitrile, sulfonic acid, acid chloride, nitro, etc. Let us now learn about pi bond lone pair orbital conjugation. There are certain molecules in which there is conjugation of lone pair of electron present over atom with pi electrons present in multiple bond. Such a group which increases electron density over adjacent group via the pi bonding framework is described as having a plus m effect. For this effect, the atom attached to vinyl carbon must have at least one lone pair of electrons. For example, if groups such as OH, OR, NH2, NHR, NR2, etc. are attached to any multiple bond, then these will exhibit plus M effect as you are seeing on the screen. Plus M effect possessing groups are shown on the screen. Let us now have a look at minus M effect possessing groups shown on the screen. They are CHO, CO, CN, NO2, SO3H, etc. We now come to the applications of resonance effect. The reactivity of benzene ring in electrophilic substitution depends upon plus M or minus M effect of the group present over benzene ring. Groups with plus M effect increases electron density over ring and are called activating groups. Similarly, groups with minus M effect decreases electron density over the ring and are called deactivating groups. Similarly, the stability of many intermediates can be explained on the basis of this effect. Let us now learn about hyperconjugation. This is an unusual type of conjugation in which there is participation of sigma electrons of CH bond with pi electron system of multiple bond. In this conjugation, there is overlapping of sigma bonding orbital of CH bond with either vacant p orbital of positively charged carbon or with p orbital forming pi bond. Hyperconjugation occurs only if the sigma bond and empty p orbital have proper orientation. Achieving proper orientation is no problem in this hyperconjugation, as there is free rotation about carbon-carbon sigma bond. In canonical forms which involve hyperconjugation, there is no bond between the carbon and hydrogen, and therefore this effect has also been called no bond resonance. Alternatively, in this conjugation, the molecular description is that this effect arises from the overlap of sigma orbitals in the alkyl group with the pi system. The evidence for hyperconjugation is that in propene, the carbon-carbon single bond is slightly shorter than in ethane. Thus, it is reasoned that carbon-carbon single bond in propene acquires some double bond character due to hyperconjugation. Moreover, the heat of hydrogenation of propene is less than that of ethene.
Hyperconjugation. This type of interaction has been shown to occur between the pi electron system and the adjacent CH sigma bond. Let us first have a look at the structure of the ethyl carbocation. Observe that a bond angle of 90 degree is formed between pi orbitals. Now observe that a bond angle of 109.5 degree is formed as shown on the screen. Three CH bond angles are 109.5 degrees, which are highlighted in white. On the left hand side, you will find that angle of 120 degree is formed where carbocation is formed. Now we have an sp2 hybridized carbon and an sp3 hybridized carbon. The empty pi orbital, which is electron deficient of the ethyl carbocation, has been shown to overlap with the adjacent sp3 s sigma bond formed between carbon and hydrogen atoms. Notice that the hydrogen atom becomes positively charged. Now, if we rotate one of the sp3 carbon atom, the aligned CH sigma bond overlaps with the vacant orbital. Let us now learn about the relative stability of carbocations. In case of a methyl carbocation, all sigma bonds are perpendicular to p orbital. Let us have a look at them one by one. There is no possibility of overlap. Let us now take the example of ethyl carbocation. It contains an electron deficient orbital. It can form three stabilizing interaction with sigma bonds. Have a look at the sigma bonds labeled as 1, 2, 3 on the screen. This means that it is more stable than the methyl carbocation. Let us now have a look at the structure of isopropyl carbocation. It forms 6 stabilizing interactions with sigma bonds. Let us have a look at the sigma bonds one by one. Let us name them 1, 2, 3, 4, 5 and 6. So we know by now that this structure is more stable than as compared to ethyl carbocation. Let us next have a look at the tertiary butyl carbocation structure. 9 stabilizing interactions are formed with sigma bonds. Let us again have a look at them one by one. This means that this structure is more stable than propyl carbocation. Let us next have a look at hyperconjugation in alkenes. Let us observe the structure of propene. Notice that the 2 electrons in the pi cloud moving. CH3 here is an electron donating group. The shared pair of electrons move to the terminal carbon. Have a look at the electron deficient orbital which overlaps with the adjacent CH sigma bond of CH3 group. 3 hyperconjugate structures propene are formed. Observe each one carefully on the screen. A double-headed arrow between them shows that these can be interconverted from one form to another.
Let us now learn about applications of hyperconjugation. We will first discuss about stability of carbonium ions. The order of stability of different alkyl carbonium ions is as shown on the screen. The order of stability on screen can be explained by hyperconjugation. In general, greater the number of hydrogen atoms attached to alpha carbon atoms, the more hyperconjugative forms can be written, and thus greater will be the stability of carbonium ions. In the structure shown on the screen, 9 equivalent forms can be formed in case of a 3-degree carbonium ion. In case of a 2-degree carbonium ion, 6 equivalent forms can be present. Similarly, in case of a 1-degree carbonium ion, 3 equivalent structures can be formed. Let us now discuss about the stability of free radicals. Stability of free radicals can also be explained as that of carbonium ions as shown on screen. Let us now discuss the third point, which is orientation influence of methyl group. The ortho-para-directing influence of the methyl group in methyl benzenes is attributed partly to inductive and partly of hyperconjugation effect. Let us have a look at the structures on the screen. The role of hyperconjugation in ortho-para-directing influence of methyl group can be shown by the fact that in nitration of para isopropyltoluene and para tertiary butyltoluene, the nitro group is introduced in the ortho position with respect to methyl group and not to isopropyl or tertiary butyl group. Although the later groups are more electron donating than methyl groups, that is, the substitution takes place contrary to inductive effect. Actually, this constitutes an example where hyperconjugation overpowers inductive effect. Children, today we have learned about the different electronic displacements which occur in organic compounds. These electronic displacements play a very important role in reaction mechanism and thus prediction of products. So, we have come to the end of today's topic. Let me now ask you a few questions to check your understanding. My first question is, why trichloroacetic acid is stronger acid than acetic acid? And the answer is, chlorine is an electron withdrawing group which stabilizes the anion formed by trichloroacetic acid by decreasing the negative charge, where, as in case of acetic acid, methyl is electron releasing group which destabilizes the anion by increasing charge intensity. Therefore, trichloroacetic acid is stronger acid than acetic acid. Next question is, why allylic free radical is more stable than propyl free radical while both are primary free radicals? And the answer is, allylic free radical is resonance stabilized while propyl free radical is not resonance stabilized. Next question is, give the order of stability of the following carbocation shown on the screen: methyl carbocation, ethyl carbocation, N-propyl carbocation, isopropyl carbocation, tertiary butyl carbocation? Answer is the decreasing order of stability is shown on the screen. The decreasing order of stability is tertiary butyl carbocation, isopropyl carbocation, N-propyl carbocation, ethyl carbocation and methyl carbocation. In ethyl carbocation, methyl group donates electrons by plus I effect. As the number of methyl group increases, distribution of charge and hence the reduction of charge density on carbon bearing positive charge is more effective. So, tertiary butyl carbocation is more stable, most number of alkyl groups more stable. Next question is, give the relative order of stability of carbanions, methyl, ethyl, isopropyl and tertiary butyl. And the answer is, the decreasing order is methyl, ethyl, isopropyl, tertiary butyl. The order is opposite to that of proposed for cations. Plus I effect of alkyl group increases the negative charge on carbon. Electron releasing groups destabilize anions. My next question is, which among the following is most acidic? Answer is, as the inductive effect of fluorine decreases with distance, A will be most acidic because the carboxylate ion which results after the loss of hydrogen ion can be stabilized by electron withdrawing nature of fluorine, which is strongest in which fluorine atom is at alpha carbon. My next question is, write the following alkenes in increasing order of their stability with explanation. The alkenes are shown on the screen. R2C double bond Cr2, R2C double bond CHR, R2C double bond CH2, RCH double bond CH2, CH2 double bond CH2. And the answer is, let R is equal to CH3. In the first compound ethylene, which you are seeing on the screen, there is no alpha hydrogen atom and there is no hyperconjugation. When one of the hydrogen atoms of ethylene is replaced by a methyl group, we find that 3 alpha hydrogens are present and 3 hyperconjugative structures can be formed. In the next case, we find that 2 methyl groups, when replaced by hydrogen atoms in an ethylene molecule, will have 6 alpha hydrogens and 6 hyperconjugative structures. When 3 terminal hydrogens of ethylene are replaced by 3 methyl groups, we find that 9 alpha hydrogens are present and 9 hyperconjugative structures are formed. In the last case, when all hydrogens of methyl group are replaced by methyl groups, 12 alpha hydrogen atoms are present and 12 hyperconjugative structures are formed. Next question is, write all possible structural isomers of the compound with molecular formula C4H10O. And the answer is, total number of structural isomers is equal to 7. Have a look at the structures on the screen. Next question is, in phenol, almost 100% enol form exists. Why? And the answer is, in phenol, there is almost 100% enol form because it retains the aromaticity of the ring, but in keto form, the aromaticity of the ring gets ruptured. My next question is, In which of the alcohols shown on the screen, CO bond breaks heterolytically with greatest ease? And the answer is breaking of CO bond results in formation of more stable tertiary carbocation. So, answer C is correct. Next question is, which of the following carbocation shown on the screen is least stable? And the answer is positive charge is on sp hybridized carbon, that is B is correct. So, I hope that you all have enjoyed today's lesson and must be able to solve some more related problems. Thank you students for the attention you have paid in understanding these concepts.